Okay, so this is the last one for materials. Okay, you can write that down. Young's modulus. Got that? Yeah. Ciao. Yep, yep. Okay, so couple of definitions first. So does anybody know this word? Deformation. What it means? Do you think you know, or what would you explain it as?
It's deformed, it's changed.
Say again?
Disintegrate.
Oh, like disintegrate, or what did you say? It changed.
Diversion shape.
Yeah, so like when we use this word, we kind of mean like a change of the shape has taken place. You know, it's a verb. Deform is a verb. It means like to. No, it's not quite disintegrate, because disintegrate means like you've destroyed it, whereas deform just means you've changed it a little bit. So we say the deformation of a material is a process of changing the shape, and for us that means the length. So you know, if you have a string, to deform it means to stretch it by means of a stressing force. Got that written down? Ciao? Almost okay. Yeah. Okay. Good. Good. So next now, the word stress. You might know this word stress in English. Yeah. It doesn't have the same meaning in physics. So when we say the stress on a material, what we mean is the force on the material per cross-sectional area. So actually, as a formula, it's stress is force over area. Now, I just want to draw a little picture to show you what that means. So, like, for example, I don't know, what, there's a person. So maybe there's a force pushing down on his head on this area here, area A. The stress is the force over the area. I could do a better example, not a person's head. I know, like say you had a rope. So this is a rope here, and maybe you have some force pulling down on it. Okay, the stress is the force over the area, and it's the cross-section area. So it's like this area. Yeah. It's a lot like pressure, isn't it? Like it's. In fact, what's the units for stress? It's pascals, because it's newtons per meter squared. So you'll need this definition. So the units is definitely pascal. You got that? Is this a word you've seen before in physics or only in English? You've seen it before?
Yeah.
Yeah. Okay. Continue, Chad? Yep. The next one is called strain. So this is also a word you would know from English. The strain on the material is the change in length over the natural length. So, in other words, as a formula, the strain is just the extension over the natural length. Oh, we're all sleepy. Not enough weekend, huh? Chow seems like the only one awake. What time do you go to sleep at, Chow?
1 or 2 o'clock, I think.
Oh, that's kind of late.
Yeah, you know why?
Why?
I'm look awake. I was during my sleeping. How can I say that? I dreamed.
Yeah?
Uh,
Bad dream?
I dreamed my ex-girlfriend.
She kill you? What happened? That's a nightmare, isn't it?
Not exactly.
Not exactly, okay. Let me guess, 3 a.m. for you?
12?
12? How come you're so tired then? Dunno. Kim?
I slept like, 17 hours.
What? That's a long time.
I know.
You must be very tired.
We were sleeping before yesterday.
Anda?
11:25.
Should be the most awake. Alright, we got this strain? Yeah. So, oh yeah, can you see that the strain has no units? Because this is meters and meters, so no units for strain, no units. Okay. Now, Young's modulus. So what is Young's modulus? It's a relationship between stress and strain. It's different for each material. So Young's modulus is the ratio of stress to strain. That is stress divided by strain. That's Young's modulus. And it's different for each material. And its units, what's the units for stress? Do you remember?
Pascal.
And strain?
No unit.
So, what's the units for Young's modulus? Pascals, yeah. Clearly pascals. You got that? Chow? Yeah? I'm actually, it just reminded me of something here. How do you guys say this word?
Tuesday?
Say again?
Tuesday?
Yeah, okay. So you know here we say this as Tuesday. You know, it sounds like a C at the start.
Oh.
Have you noticed this?
Tuesday.
Yeah. We make it sound like Tuesday.
Tuesday.
Yeah, like this.
Yeah.
Tuesday.
Tuesday. Yeah. So I'm wondering, how do you say this word?
Ratio.
Yeah.
Ratio?
That's how we say it anyways. I was just wondering,
I
with
always
the
think
T.
about that is the route.
No,
Lorraine says
not ratio.
Ratio.
What does Lorraine say?
Ratio.
Yeah, that's what I say as well. Ratio. Yeah. Now I'm just wondering, because the T, you know, it's a difference between American and Irish English. So Americans would say Tuesday, and we would say Tuesday. But, what? What's so funny? Okay. Right. So that's Young's modulus. Now, we'll talk a little bit in a minute about what Young's modulus means. But before we do that, I'm afraid we need more definitions. Lots of definitions. So, tensile strength. Does anyone know? Well, does anyone know tensile strength? Yeah, you can use it in the ropes. What's its meaning when you're talking about ropes?
How strong it is when you stretch it.
Yeah, nearly. Yeah, it is a strength. So just to be more precise, it's the force required to pull something like a rope or a wire or whatever, or a structural beam, to the breaking point. So it's how much force you need to break something, really. So for example, the tensile strength of bones is how much force you would need to break your bones. Tensile strength is important. Well, what part of engineering do you think is most important, tensile strength?
The wire?
Yeah, but like in day-to-day life, where do you think it's most important? Say again? Yeah, like give me an example. Like you're right, civil engineering. So which thing do you think in civil engineering? Yeah. Don't be shy. It's just your opinion. I'm just wondering what you think is most important.
Like those things that they build with, like it's hung by a rope, and
This is like on the construction site. Yeah. Do you mean the cranes that lift up things, or? Yeah. So you want to know how much you could lift before the wire breaks. I think for me, one of the most important things are bridges. Just because you don't really want your bridge to collapse. But the reason I say this is because you know, like in a modern bridge, it's built out of steel and concrete and materials like this. So these are all modern materials. And what's nice about these materials is that the tensile strength is known for these materials. So you know what the tensile strength is for steel. You know what the tensile strength is for concrete. You know when they'll break, okay? One problem though in Ireland, so this is an Irish type of problem. I don't know if you've ever seen these these old stone bridges. So they're little bridges. They're not that big. You'd see them in the countryside. You know, they'd only be like 3 meters long, and they'd just be like a stone humped bridge like this. And it's made of stone, only stone, no steel, no concrete, because, you know, it'd be like whatever, 200 years old or something like this. Have you ever seen these bridges? But you can imagine them, these little stone bridges. So anyways, I was watching a TV show, and they wanted to know what is the tensile strength of the stone bridge. They wanted to know when would it break, you know, because they don't know. So many of them in Ireland. So they got permission to break one of them. So what they did was they got these huge, really huge, like hydraulics, and they would push them in. They connect it to the bridge and they push it in, and what they would do is they would increase the force, and they would increase the force until this would break, and then that, of course, is the tensile strength. Okay, so increasing for the whole day until the machine reached maximum force and the bridge didn't break. So this tensile strength, whatever it is, it's so big that they weren't able to figure it out. Now, just to let you know how much force that is, I think they said something like, you know, these big HGV trucks, you know, for deliveries. The force on it was the same as I think it was 100 of these on top of the bridge. So that means this bridge is pretty safe because it's not big enough to hold one of them, so there'll never be 100 on them. So you know, this will be much safer than the bridges in the city centre, which is quite amazing when you think about it. It's just made from stone. Okay, so tensile strength, it's quite interesting. Like we were talking about the aeronautical, you know, the planes. You want to know how much force the steel can take, all this type of stuff. So this is very interesting civil engineering stuff, and also it works for ropes and things like this as well. Okay, so I want to have a look now at the stress-strain graph compared to the force extension graph. Okay, so right, let's have a look here. So this graph here is stress, and this one here is strain. So this is something like, let's say you have, I don't know, maybe you have a rope, and you pull down on a force, and you measure the extension, and you know what the original length was. So you can calculate the strain. The strain is X over L. Now, the stress is the force divided by the area. So what happens, do you think, if I make the strain bigger? If the extension is bigger, what do you think happens to the stress? The pressure, what do you think happens? Bigger or smaller? What do you say? Other way, bigger. Because what happens here is if you want more extension, you're going to need to pull it down more, which means you need more force, which means then more stress. Yeah? Oh, do I have this backwards? Sorry, what did I... Japers. Confused myself because I'm tired. Strain is the extension one. Excuse me. Right, let me... Oh no, I did have it right. Okay. So, the graph, if there's no strain, there's no stress. And you increase the strain, you get more stress. Okay. Can you see how this is a lot like Hooke's graph? You know, if here you have extension and here you have force, what happens when you have more extension? More force. So it's actually very similar. In fact, I want to show you exactly what the relationship is. So, Young's modulus is stress over strain. So that means the slope here is equal to Young's modulus. And what did we say the slope here was? Is equal to K. Good, okay, so let's see what we get here. Stress is force over area, and strain is extension over length. Well, what did Hooke say force was for a stretchy material? Kx over area over x over length. So the x's cancel, so you're left with K over A over L, which is A over L K. So you can actually see that Young's modulus is area over length times K. In other words, Young's modulus is proportional to Hooke's constant. So basically, they're not that different. If the K is bigger, then the Young's modulus is bigger. If the K is smaller, then the Young's modulus is smaller. What is a big difference between the K and the E, though, is the K doesn't care about the shape, whereas the Young's modulus, you care about the shape. You need to know the area and the length. So you need to know how big this is and how long it is. Whereas with Hooke's K, you don't care about these things. Okay? So that's why we need Young's modulus, because it's a bit more realistic, because we do actually care about, for a rope, how big the A and the L is. Okay? What I really just need you to write down is maybe everything. Let me get rid of this little picture here. Here's my pen. Question, Kim? You can ask me.
Isn't it supposed to be like K over AL?
Did I make a mistake with my fractions? Thank you. Ah, you're right. Thank you very much. The A... Thank you. I went to sleep at 2:30, you see. Get my pen back. 1 over AL. 1 over AL. Okay, I actually do think I need you to write all of this down. It's important, so... This graph is for Young, and this one here is for Hooke. Now Chow's getting sleepy, like everyone else. I thought school starts early in China. Starts at 8 o'clock?
High school?
Yeah.
I can't remember because I always late.
Ah.
You see now?
Some things don't change.
Yeah, yeah.
Some things don't change. School starts early in Korea. This is 8 o'clock. This is 7. Oh man.
Yeah, maybe 7.
That's terrible. And what time does it finish at?
9 sometimes.
Yeah.
Mine was 11.
Really?
Late? Yeah.
How whole day?
Yeah.
more than 12 hours.
That's terrible.
Yeah.
Terrible. Tough life. Tough life. Alright, have you got this, Andek? So then 9 o'clock to 5 o'clock should seem easy peasy. Now for you, Siva?
Exactly. Because in high school I was young and I was
Okay, yes, you're right.
And now I'm almost 13 years old.
Ah, that's still young. What are you talking about? Look, Andek is only, you're 17, aren't you? Yeah, it's not like he has lots of energy either, right? He's just as sleepy as you. Yeah. Yeah. Okay, continue? Yeah. Right. Okay, so I want to give you some values of E for different materials, and in the exam they'll give them to you if they need you to have it. So just remember, if the E is big, it means the K is big. And how would you describe a material with a big K? What would you say it is like if the K is big? Do you remember? What do you say? Yeah? Like you can either say if the K is big, it's either very stretchy or very, very stiff. Yeah. So what would you say, stretchy or stiff? Ah, the other one, yeah. If the K is big, it means it's very stiff. If the K is small, it means it's very stretchy. Yeah? So the same for Young's modulus. So the first material is rubber. So rubber, you know, is very stretchy. So 0.10 times 10 to the 9 pascals. Now, remember, this is a small value, even though it's 10 power 9. That's considered a small value. Okay, the next one, nylon. 2 times 10 power 9. Now, who knows what this material is? Yes. I'd expect you two to know what it is. Yeah, you two. Nylon. Do you know? It's related to clothes, yeah. It's the fabric used to make tights. You know tights? Yeah. So you know that this is like rubber. It's stretchy as well. So this is also a small value then. Okay. But I think it's sometimes nylon is sometimes mixed into, like maybe your sweater, because it's kind of stretchy, might have some nylon mixed into it because it's got a stretch to it. And maybe like your sweater and your sweater, these have nylon in as well. It's an artificial, man-made fabric. Yeah. I think you can actually check your tag.
Sorry?
You got your tag to check? Yeah, we'll see. They put nylon in clothes to give it a bit of a stretch. Let's have a look.
It is made in China, that's it.
That's all you know about it?
That's all they have.
That's all the info? It doesn't say what...
They have to check.
Oh good, yeah. We'll have a look there.
Everything made in China.
Arabic word?
Ah, no English?
Yeah.
Let's have a look. Never? Then how do you know how to wash your clothes?
Just put in the washing machine.
I can't read Chinese.
Does it say how to wash it?
Fantastic.
Yes. There's the washing instructions here. You've learned something new, huh?
You put on the dog first.
No, it doesn't. I can't see it's in Chinese. It doesn't matter. Let's feel it. I think, well, maybe not actually. Maybe a little bit, 5% or something. I think nylon might be based off of a plastic. It might be a type of plastic, I think, because you know when you recycle like your plastic bottles, like that bottle or that bottle, that doesn't get recycled to make a new bottle. You might think when you recycle that it becomes a new plastic bottle, but the problem is when you recycle plastic it loses its quality. It's not as good quality. So plastic bottles get recycled into clothes. So I think maybe it gets recycled into nylon. I think so. And then when you recycle your clothes, it doesn't become clothes again because the quality drops. It becomes carpet. So this carpet will be made from recycled clothes, which was made from recycled bottles then. But then when the carpet needs to be recycled, you can't. Because the quality is so low now, there's no point in recycling it because you can't make it into anything useful. Okay? This is why plastic is really terrible. Plastic is really, really bad because it just doesn't recycle well. Okay? If you had metal, you can recycle it back into metal. You have wood, you can recycle, or paper, you can recycle into paper. Glass again. But plastic, every time you recycle it, it goes down a level of quality. So that bottle, you know, it can only be recycled once into clothes and once into carpet, and then, you know, then this has to go into a dump. You know, so the plastic is not great. It's better to have metal cans or glass bottles. You know. Okay, next material is wood. So wood is pretty stretchy. It's not too bad. You can stretch it a little bit. The only thing about wood is if you want to stretch it, you have to do it slowly because you can break it. But you know, when they're making furniture, they can stretch the wood a little bit to kind of lock it into place. Okay, next material is glass. Now you can see we're starting to get much bigger now. Glass obviously isn't that stretchy. Okay, next material. Brass. And then next material, copper. So next material, steel. And now the stuff in the pencil, the graphene. Is anyone using a pencil? You're all using pens. Yeah, you know the stuff in the pencil. That's this. Yeah, the inside. Yeah, that part. Yeah, that's a form of carbon. Have you done it in chemistry? This material, this.
A bit.
A little bit. You've heard of this word before?
No,
Graphite, yeah. And yeah, that's all actually. Now, it might surprise you to actually see there, Andek, for your pencil. The graphene is actually stiffer than steel. So it means that, you know, you can't really easily change the shape of it. You can't stretch it.
But you can break it easily.
Yeah, that's usually an interesting relationship. When the material is very stiff, it's more likely to snap. Because it's so stiff, it can't stretch. You know? Yeah, so you're right. So the pencil snaps because it's so stiff. It's the easiest thing in the world to snap, isn't it? Like, if everything that will snap It might be the top of the pencil. Yeah. Okay, so let's have a look at some examples here. Just the one example, actually. Okay. A boy, back to the boy hanging a 100-gram mass at the end of a 1.5 meter copper wire, which is attached to the ceiling. The wire is 2 millimeters thick. Now, I think we can do this one together. I think I can let you do it bit by bit, because if you look what's happening here, I'll draw it for you. So you've got a piece of copper, the copper wire. Now, it's only 2 millimeters thick. So that means here the cross is 2 millimeters. It's 1.5 meters long. And there's a 100 grams hanging at the end of it. So my first question is, what is the area? So I want to know, what is this area here? Now, I think you all know how to get that. What shape is this?
Rectangle. Oh.
Try again, Andek.
Sorry.
Yeah, go ahead. What is it? Circle then. So the area is pi r squared. Now, do you know what the r is? 1 millimeter. Millimeter. Okay. Can you give me the area?
Do you have to convert it to meters?
Oh yes. Yes indeed. Okay, you should have gotten something like 3.14 times 10 to the minus 6
Yes.
meters squared. Yeah. Kim, is that okay? You're not looking too happy with this. Is okay? Are you sure? Okay. Part 2. What is the stress? Okay, so what's the formula for stress? What's stress formula?
Force over area.
Force over area. Now, we know the area. Who can tell me what the force is here? What's the force for this problem?
Um, 0.1 press G.
G. Yeah. In other words, what's causing the force? The mass, the weight. So it's the weight, isn't it? Which is mg over the area. Okay, I'll let you calculate that now. So let me see, that would be 0.981 over 3.14 times 10 to the minus 6. So that should be a pretty big number. What did you get here, folks? Okay. 10 to the 7 or something?
Oh, 3, 1, 2, 4, 2, 0.
3, 1.
2, 4.
Yeah.
2, 0.
Yeah.
3, 8.
Okay. That's not as big as I thought. So we'll say that's 312,000 pascals. Okay? Right, part 3. what is the strain? Now, what's the formula for strain? It's extension
Over length.
over length. Now, do we know the natural length?
Yeah.
Yeah, it's 1.5. Do we know the extension? No. So we shall need another formula. We can use the formula Young's modulus is stress over strain. Because we know this, it's copper. So I gave you that value. And we know this. So we can say strain is stress over Young's modulus. What was the Young's modulus for copper? Yeah, 170. 117 times 10 to the 9. Okay, so let's get the strain. Uh-huh.
Times 10 power 12.
Where did the 47 from 10 to 12 like come from?
The what?
The 47.9?
47.9.
47 times 10 to the power 9.
117.
Oh, the 117.
Sorry.
What? Looks like a 4.
From my point of view, it does.
Maybe. 117. Okay. Is it okay so far? Let's see what's next now. So, next part is extension, I'd say. By how much does the wire extend? So, that's the x. So what we can do is we can now use this formula because we know the strain, we've worked it out, and we know the length here. See, but are you sure that's right? I feel like it should be a minus 12 or something. Yeah? Something right. I'm going to go with Kim's answer here. -6.
Yeah.
Yeah? Yeah? Okay. So, if I use this formula now, strain is extension over length, I can work out the x, the extension, because I can say x is L multiply strain. So that is 1.5 multiply 2.667 times 10 to the -6. So what is that going to be now? 8 over 3, 12 over 3, 4. Is it 4? Times 10 to the -6 meters, which is 4 micrometers, which is not much. Can't even see that. 4 micrometers. Okay, 5, or E I should say. What is the K for this wire? What's the K? Alright, so oh, actually, I just realised I don't have my plug in and the battery's probably about to go. What? Let's try that again. Okay. So I want the K now. So if you remember, I said.
Sorry, you just spoil a bit.
Oh.
Sorry. Wait.
You just need this part, is it?
Yeah.
So I said Young's modulus is stress over strain, which I said is force over area, extension over length. Isn't that right? So that's Kx over A over X over L. So that's K over A. Oh, I made a mistake, I think, in my proof earlier. So, Kim, you noticed my mistake here, but that should have become 1 over L. Yeah. Okay. Right. No matter. We'll fix it here now, okay? So, I made 2 mistakes, which meant my answer was actually right the first time. So this should have been 1 over L. So then this is L over A K. Okay, so anyway, K equals A over L E. So that would be, what did we say the A was? 3.14 times 10 to the minus 6. That's 1.5. And what was the E? It was 117 times 10 to the 9. Okay, so what's that? And then that's this question finished. Two, four, four. 920 newtons per meter. Okay, did you write that down? How are the questions? Okay. I think you'd be okay with these. Do you need me to close the window? Are you cold? Nice fresh air? Okay, so what time are we at? About 1:30. Right, if you try these for 10 minutes and then we'll finish materials and we start electricity tomorrow. So just try these for 10 minutes and then you can have your breakfast. Because I know you don't have breakfast yet and you didn't have breakfast yet. And you had breakfast?
Just like a chocolate bar.
Okay. Breakfast?
A little bit.
Oh, good. Good. Okay. So try these for 10 minutes and then you can take second breakfast.